So before we start with the chapter 1 on sinusoid and phasor, I'm going to do a revision on the complex number. So let's look into this. What is complex number? So complex number can be represented by using rectangular, polar, and exponential form. So in mathematical operation, complex number can do addition, subtraction, multiplication, and also division, similar like the normal numbers. So let's look into the rectangular form of the complex number. So if you look at this is the rectangular form. So z is equal to x plus jy, y, where x is the real part and y is the imaginary part. And in this complex number, j can be identified as square root of minus 1. So how we can represent this rectangular form into a graph. So basically this complex number is a point here z, so we can represent this. X is at the x-axis, the real axis, while the imaginary axis y is at the y-axis. At the same time, complex number can be represented in polar form. So in polar form, z is equal to r theta. So r is the magnitude while theta is the angle. So it can be represented in the graphical figure like this one. So r is the length of this red line here, while theta is the angular between the x-axis and the r line over here. So if you want to get r from the rectangular form, we can get it by using the y and x. So to convert the rectangular form to polar form, so you can use this formula. So to get r, the magnitude in polar form, you can use the equation square root of x power of 2 plus y power of 2. So x is the real part and y is the imaginary part. While to get theta, you can use inverse tangential y over x. So at the same time, you can convert from polar form to rectangular form using this equation. So x, the real part of the rectangular form, is equal to r cos theta, while y is equal to r sin theta. Representation that you can use for complex number is using exponential form, where z is equal to r ej theta, exponential j theta. So in summarize, we can represent the complex number in three kind of forms: rectangular, polar, and exponential form. So this is the important facts that you need to know. You can use your calculator, scientific calculator, to convert from rectangular to polar and also polar to rectangular. But the first step, you need to set your scientific calculator to the correct mode, which is first you need to press mode 4 times to change it to degree. Here, choose one, which is the degree, and the step 2 is to change the mode for complex number. So you need to choose complex, which is choose 2. So this setting need to be done before you can convert rectangular to polar or polar to rectangular form. So for rectangular form, the J can be represented as I symbol in the scientific calculator. And to convert from rectangular to polar, you can use shift and followed by plus symbol. Basically, there's a symbol on your scientific calculator. You better explore it by yourself, how to convert rectangular to polar and polar to rectangular, and make sure you need to be familiarized with this kind of method. So let's look into the mathematical model operation. So for complex number, you can do additional and subtraction. So for this, you have to for additional and subtraction, you need to do in rectangular form. For example, addition and also the subtraction. However, if you're using calculator, it doesn't matter whether you use rectangular or polar form. You can still add or subtract the equation. And for complex number, for multiplication, so you can use it's better for you to use in polar or exponential form, where you have magnitude and theta. So the equation is like this for multiplication. And also for division, you have to use in a polar or exponential form. So for this, I suggest that for addition, subtraction, multiplication, and division, I suggest that you use more scientific calculator to do the operation. Other than that, we need to know about the complex conjugates. So how do you want to identify the complex conjugate? The complex conjugate is identified by symbol star. So if you have a Z star over here, for example, like this, so this is the complex conjugate. So this is an example. Z is equal to 3 minus J4. So to change this complex number to complex conjugate, we have to change the or to replace the J here to minus J. So if you change to minus J, this operation will change to positive, from negative to positive. That's how to, if you want to change a complex number to complex conjugate, and can be identified by the star by the star symbol. Other than that, you also need to know the Euler's formula. So this is the example of the Euler formula. E j theta equal to cos theta plus j sin theta. So from this equation, you can get other equation for complex variables. So this is an example of it. So that's all for revision for the complex number. I hope that you understand how to convert from rectangular to polar, and also do the operation subtraction, additions, multiplication, and division. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. So now we're going to chapter 1, Sinusoid and Phasors. So this is the contents of the chapter. So we're going to discuss on introduction, sinusoid, phasor relationship for circuit element, impedance and admittance, and also impedance combination. So some introduction on the history of the sinusoid and phasor or AC current. Historically, DC sources were the main means of providing electric power until the late 80s. At the end of the century, the battle of direct current versus alternating current begins. So both had their advocates among the electrical engineers of that time, because AC is more efficient and economically to transmit over long distance. AC system ended up the winner. So a sinusoidal current is usually referred to as alternating current or AC. So circuit driven by sinusoidal current or voltage source are called AC circuit. So we are interested in sinusoid for a number of reasons. First is nature itself is characteristically sinusoidal. Second, a sinusoidal signal is easy to generate and transmit. Third, through Fourier analysis, any practical periodic signal can be represented by a sum of sinusoid. And lastly, a sinusoid is easy to handle mathematically. So this is basically a sinusoid. It is a sinusoidal waveform with the y-axis is the amplitude, while the x-axis is the time or the angular frequency. So the periodic time t is a complete waveform, sinusoidal waveform. So a general expression for the sinusoid is Vt equal to Vm sine Wt. So Vm is the amplitude of the sinusoid. For example, if you look at this figure, so the peak of the sinusoidal waveform is the Vm in y-axis. And W is the angular frequency, which the unit is radians per second, and Wt is, we call it argument of the sinusoid. So W is basically depends on the x-axis of the graph. So it can present as Wt or T in the x-axis. So it is evident that the sinusoid repeats itself every t second. Thus t is called the period of the sinusoid. So the period t of the period function is the time of one complete cycle, or the number of seconds per cycle. As I mentioned before in the previous slide, there's a period t which completes complete set of the sinusoid waveform. So the equation is t equal to 2 pi over w. Other than that, we also need to know this equation, f equal to 1 over t. T is the period of time and f is the frequency. So from these two equations, from this slide, the equation in the slide and also the previous slide, we can conclude that W, which is the angular frequency, is equal to 2 pi f. So f is the frequency in hertz and W is the unit. The unit is radians per second. So let's look into this two sinusoid. So we have two equations, V1t equal to Vm sine Wt and V2t equal to Vm sine Wt plus phi. So the difference between these two equations is the phi here. So if we represent this equation into graph, you can have this kind of graph. So the first sinusoid is the straight line here, and the second sinusoid is the dotted line over here. So The difference between these two sine wave is the phase difference, which is the phi over here. So the starting point of V2 occurs first in the time with difference of phi here. And if the phi is equal to 0, V1 and V2 are out of phase, while if phi is equal to 0, if phi is not equal to 0, V1 and V2 are out of phase, while phi equal to 0, V1 and V2 are in phase. So this is a sinusoid where we can express in either sine or cosine form. So for example, sine Wt plus or minus 180 degree, we can it is basically equal to minus sine Wt. So this is trigonometric identities which relates between sine and cosine form. So let's look into an example. So from this equation, find amplitude, phase, period, and frequency of the sinusoid. So we know that amplitude is the is 12 because it is at the front of the equation, and the phase or phi here is the 10 degree. The angular frequency is W, which is usually paired with the T. So this is the angular frequency 50. The unit is radian per second. And to get F, you need to find the period T first. So T is equal to pi over W. So insert the angular frequency value into W, you can get 0.1257 and convert it to frequency using this equation. Then you get the frequency is 7.958 Hertz. So another example, you can do it yourself and check the answer, is it correct or not. So let's look into the phasor. So phasor is one of the way how we can represent the sinusoid or sinusoidal wave into a different kind of form. So this is an example of a sinusoid. So from this sinusoid, we can represent into phasor like this one. So for example, at this point here, you have the peak amplitude with the phase or angular frequency at 90 degree. So we can represent it as a phasor in this kind of form over here. So a phasor is a complex number that represents the amplitude and phase of a sinusoid. So it gives only amplitude and phase. And a phasor provides a simple means of analyzing linear circuit excited by sinusoid source. So to analyze a linear circuit, it is better to use in phasor. So the idea of phasor representation is based on Euler's identity. So how we can convert from the sinusoid equation like this one into a phasor equation? So you can use this kind of formula. So for example, we have Vt equal to Vm cos Wt plus phi. So we can represent the Vt equal to real V E J W T, or we can write it like this. So V is equal to Vm phi. So for the voltage, we can represent, or it's basically equal to Vm phi, which will represent it like this on the leading direction, while the current I is equal to Im minus theta, which is lagging behind the voltage. So that's why the value here is negative theta. And you can see that the phasor is different. For voltage, you use phi, while for the current, you use theta. So to get the phasor corresponding to a sinusoid, you first express the sinusoid in the cosine form so that the sinusoid can be written as the real part and complex number. Then we take out the time factor EJWT, and whatever is left is the phasor corresponding to the sinusoid. So by suppressing the time factor, we can transform the sinusoid form from the time domain to phasor domain. So this is the equation for sinusoid. We call it time domain representation. So to convert to the phasor domain representation, we just remove the time factor. So the parameter that left is Vm and also the phi here. So this is represented as the phasor domain. So for sinusoid phasor transformation, you can refer to this representation. For example, Vm cos Wt plus phi, you can represent it as Vm phi, while Vm sin Wt plus phi, so the difference is the cos, sine and sine. So for the phasor domain, Vm phi minus 90 degree. So similar to the current equation. So in phasor, differentiating a sinusoid is equivalent to multiplying its corresponding phasor by JW. So this is the representation. However, for integration, a sinusoid is equivalent to dividing its corresponding phasor by JW. So like this. So in phasor, if it's a differentiation, is basically a multiplication. So what basically different between the Vt and V? So Vt is the sinusoid and V is the phasor. So Vt is the instantaneous of time domain representation, while V is the frequency of phasor domain representation. Vt is time dependent while V is not, and Vt is always real with no complex term, while V is generally complex. So let's look into an example in this complex number. The operation, we look at this 9.3a first. 40, 50 degree plus 20 minus 30 degree, square root 1 over 2 is square root. So basically you can use calculator to do the addition operation, or if you can also do it like this manually. So for me, I suggest that you just use calculator because it is much faster to do the operation. And for the square root, you cannot use the calculator. I think they will give you math error from your scientific calculator. So to solve this, for the real part, for the magnitude, you can straight away do the square root of 47.2 here. So you get 6.91. And for the phase of phi, you just divide by 2. So 25.63 divided by 2, you get 12.81. So let's look into another example. We look at A here, I equal to 6 cos 50t minus 40 degree A. So this is the current equation for the time domain representation. So you need to transform it to phasor. So to transform in phasor, you just remove the time factor. So from here you can get 6 is the magnitude, while 40 degree is the delta. So I is equal to 6 minus 40 degree ampere. So let's look into another example with operation. So we are given two equations, I1t and I2t. So the question asks you to sum these two equations. So how we want to do it? Let's look into the solution of it. So the first thing you need to do is to change the time domain representation, these two equations here, into phasor equation, phasor domain representation. So I1 is equal to 430 degree. So we got the magnitude here and the phase over here. And I2 is because this is a sine here, so you need to change it to cos. So that's why you get cos, and that's why you get minus 90 degree over here. To change sine to cos, you just minus 90 degree. So from here you will get 5 cos WT minus 110 degree. So from this equation, change to phasor. So I2 is equal to 5, the magnitude over here, and the degree is, delta is minus 110 degree. So from these two equations, you can do the addition of the sum operation of these two equations using calculator. So let's look another example. Find voltage Vt in circuit described by the integral differential equation over here using phasor approach. So if you look at this equation, there's a derivation and integration. So what you need to do, because the question asks you to use a phasor approach, you change this dv over dt and the integration v dt into the phasor representation. So to change it, dv per dt is equal to jw, while integration of v dt is v over jw. So from here, you change it to phasor representation, including the time domain representation on the right side. So from here, you will get this equation, and w is, you get it from this value over here. So after inserting all of this into the equation, so the only thing that you need to find is basically is v. So v here, you can put it out from the equation on the left side equation, and basically you can get the value of v in phasor form. So from after your division of these two equations, you get 5.3 minus 87.99 degree. So from here you change back to the time domain representation. So Vt is equal to cos Wt minus the degree from this part. So we already discussed introduction, sinusoid and phasor. So now we're going to look into the phasor relationships for circuit elements. So this is the phasor relationship for circuit element R, which is the resistor. So if you look at this, there's no difference between the time domain representation and also phasor domain representation, where the equation is the same, which is V equal to IR. So this is the phasor diagram of the resistor. If you look at this, V and I, voltage and current, is the same phase between each other. So let's look into the inductor. So what's the relationship between these two? So for time domain representation, the equation is V equal to L di over dt. While in phasor domain representation, V is equal to JWLI. So if you look at this, the difference is the derivation is equal to the JW for the phasor. So from this phasor diagram, we know that inductor has a voltage has a phase different. The voltage and current difference is 90 degree, where the voltage is leading while the current is lagging behind. So we can call it I lags V. So current lagging from voltage. So let's look into the capacitor, the voltage current relationship for a capacitor. So if we look at this time domain representation, I is equal to C dV over dt, while in phasor domain or frequency domain, I is equal to JWCV. So the derivation is converted to JW in frequency domain. So from here, from this phasor diagram, we know that I basically the current is leading the voltage, and the current and voltage has a 90 degree difference, with current leading while the voltage is lagging behind. So this is a summary of the phasor relationship. Before this, I had said phasor domain basically is actually a frequency domain. Okay, so time domain, frequency domain, and the difference between the element R, L, and C. Let's look into an example. So for this example, voltage V is equal to 12 cos 60t plus 45 degree, and it is applied to 0.1 Henry inductor. So the question asks to find steady state current through the inductor. So based on the equation that we have discussed before, the first thing that you need to do is to change this time domain representation to the phasor domain representation. So you will get this equation 12 45 degree with a 45 degree phase phi, and from here we can use equation where I equal to V over JWL. So this basically, that from this table here we know that over here, okay, because this is V equal to JWLI. So if you want to find I, means that V divided by JWL. So from here we know that the current I is equal to 2 minus 45 degree ampere, and to convert it to time domain, you can just insert back the magnitude and also the phase into the time domain representation, and the angular frequency you can use back the voltage over here.